Well, good morning, everyone, and welcome to the second part of this cycle of conferences that brings together under the title Chemistry, a Handout to Society, 11 talks related to chemistry, chemical engineering, and biochemistry. Today, on this third Thursday of the series, we will have the pleasure of listening to Agustin Molinantoria, professor from the Department of Organic Chemistry, who will talk to us about a tremendously interesting and attractive subject, not only for our scientific community, but also for society in general. Professor Molina will talk about whole transporting materials for perovskite solar cells, a chemical approach. As I usually mention when presenting these talks, we have opted for the online format instead of the face-to-face format, taking advantage of the platform provided by the Foundation General of the UCM, whom I would like to thank once again for their help and support in organizing this activity. Thanks also to our funding sources, Spanish Biochemistry and Molecular Biology Society, the Royal Chemistry Society, Sectorial of Madrid, and Vice Rector for Research and Transfer, for their financial support as enables us to use this format, which allows many more people to be connected. The choice of the language for this activity deals with the fact that the science is mainly written and discussed in English. Our junior researchers, most of whom have done their research abroad, have joined our institution after spending time outside, and organizing these webinars in English can even make it easier for them to communicate their scientific results. In this way, we can extend our audience to foreign institutions, some of which have been the host institutions for these researchers. The lecture will always take place on Thursday at 12:30, and the last one will be on June 2nd, and each webinar will be announced at the beginning of the week, including the link of the registration form. Without further ado, I will hand over to the moderator of this talk, Ángeles Herranz, professor of the Department of Organic Chemistry, who will introduce the speaker and moderate the questions that you can write in the preguntas y respuestas box that you have at the bottom of your screen, not the chat. The preguntas and respuestas box that you have on your screen. It is the turn for Professor Herranz. It's your turn.
Many thanks, Maite. Well, it is my pleasure today to introduce you Dr. Agustin Molinantoria. He joined the Department of Organic Chemistry past year as a Ramón y Cajal fellow. And Agustin has developed a scientific career in the frontier between organic chemistry and materials science along all this trajectory. He started his studies at Autónoma University of Madrid, and in 2006 obtained the degree in chemistry. Afterwards, he carried out his PhD here at Complutense University under the supervision of Professors Andrés Golumis and Nazario Martín, working mainly on molecular wires from 2007 to 2011. Subsequently, he moved to the Molecular Institute of Science in Valencia, ICEMOL, to interact for a few months with Professor Bolink, focusing at that time his attention on new materials for photovoltaics applications mainly, before traveling overseas and joining almost for 3 years the group of Professor Luis Echegoyen in the University of Texas at El Paso in the United States of America. Over there, he worked on the electrochemistry of carbon nanostructures and also on photovoltaic devices. Agustin came back to Spain, to Madrid in 2014. He joined the Organic Molecular Materials group led by Professor Nazario Martín, who shares laboratories here at Complutense University and also at INDEA Nanoscience. And over there, Agustin has been working till now in the nanoscience in particular. He has settled the photovoltaic energy laboratory. Overall, Agustin has developed a new organic, has developed new organic compounds as molecular materials for technological applications, mainly in the fields of molecular wires, molecular rectifiers, materials for organic photovoltaics. I think he has a strong background with almost 50 publications in top-notch journals. He has been engaged in the organization of several meetings related with the field of organic electronics. And as Maite already mentioned, today he's going to focus his presentation on whole transporting materials from a chemistry point of view, because he's mainly a chemist and a person who prepares new molecules for applications. So I insist, please don't be shy. Make questions through the preguntas and respuestas. Apparently, considering the instructions that we receive, I should choose the best questions and translate it. I hope we have many and I have to choose. And well, I think that with this, it's time to give the word to Agustin and enjoy his lectures. Many thanks, Agus, and go ahead. Thank you very much.
Well, thank you very much. Thank you very much. I would like to start by thanking Maite for the organization of these talks, and also for giving me the opportunity to tell my story here. And also, I would like to thank you, Maria Ángeles, for the nice introduction. So today I will talk about whole transporting materials for perovskite solar cells, and it's a chemical approach. So at the beginning, I will give you an overview of the field. I will talk about perovskites. I will talk about advantages and disadvantages, and going through different topics about lead-free, perovskite dimensionality, devices, and finally I will focus this talk on the whole transporting material that I have been doing during I joined in the nanoscience. So here I show you some of the future threats that humanity will face in the future. Some of them are related with water, some of them with pollution, and we have two of them that are more energy related. For example, climate, because the growth of the greenhouse gas emissions continues to warm the average temperature of the planet, and the population, because the number of inhabitants is still growing. It's not growing at very high rate, but it's still growing. So that means that more people needs more energy. So for example, last year, the energy demand rebound 4.6%. So why do we want to go to solar energy, or why do we want to continue developing this energy? Because we are receiving an extraordinary amount of energy from the sun, and we are not taking advantage of that. So even though our planet is in a good position, we are not in the top 5 countries with the solar panels installation. So for example, the solar energy that we are receiving from the sun in 1 hour, it is enough to the energy that the mankind is consuming globally in 1 year. Also, the sun that energy that we receive from the sun in 1 year provides almost 200 times higher the energy of the world's entire known supply of fossil fuels. So this is why we need to continue developing this technology, and also because it's free, it's renewable, and it's practically limitless. Well, until the sun explodes, but it's not expecting to happen soon. So the solar energy market is still dominated by silicon solar cells that transform this sunlight into electricity in just 20 to 25%, but present some disadvantages such as high temperature to prepare to manufacture the devices. So therefore, we need high energy requirements, and also that they are rigid and heavy weighted, so we cannot use it in facades of buildings or even in windows. There are some other technologies transforming this sunlight into 20 to 23% called thin film PV, but they are using less abundant elements, complicated structures, and they need the preparation of these devices as vacuum processing, so make them very expensive also. Here, as a curiosity, we have multi-junctions PV, with efficiencies higher than 47%, but these are prohibitively expensive. Well, there are a new way and a new materials that are called emerging thin film photovoltaics that are based on organic molecules. So, for example, we have the dye-sensitive solar cells that transport the sunlight in a 13% efficiency and consist on organic dye with an anchoring group that will anchor the titanium oxide, and then we need a liquid electrolyte, and finally we have the device and transforming, as I said, at 13%. So it seems that this technology is still stuck at 13%. On the other hand, we have organic solar cells that are basically made of a blend of a donor molecule, organic molecule, and a donor and an electron acceptor molecule. Mix them together. We have the solar cells with efficiencies nowadays of 18.2%, because in 2010, this technology seems to reach a dead end with efficiencies of 12%, are not surpassing that efficiency. But very recently, new materials appear, and nowadays this efficiency just jump to 18% efficiency. So right now, on the other, we have hybrid perovskite, hybrid solar cells that are made of perovskite that are inorganic and organic part, displaying efficiencies of 24 as high as 25.7. And we have also tandem solar cells that are made of two different perovskites with efficiencies higher than 26%. Here I show you the National Renewable Energy Lab PV chart, where the new world records for every technology in PV are collected. And if we focus on this part, we have the perovskites in these yellow dots. Originally, perovskite exhibit a very modest efficiency of 4%, but in a very short period of time, within 5 years, it reached a tremendous amount of 20% efficiency, so which is unprecedented because no other material has started so low and go so high in such a short period of time. Well, perovskite is one of the most common crystal structure found on the planet. It was originally discovered in 1839 by Gustav Rose and named it after a Russian mineralogist called Lev Perovsky. So the general stoichiometry of ABX3, and the most common structure is the cubic structure. This cubic structure is the one that is going to be active for photovoltaic applications. But this cubic structure is quite stringent to the relative ion size of the ions that made the perovskite. So to maintain this cubic structure, we have to keep the tolerance factor in between 0.8 and 1. So I will go into detail later on. So there are a large class of perovskite with promising photovoltaic characteristics, but out of those, methylammonium lead iodide was the first one made for photovoltaic devices. From the structure, we can see that we have the B cation that is typically lead, tin, or bismuth, and that is surrounded by halides in a octahedra. And then we have organic cations or small organic cations such as methylammonium, formamidinium, or even cis-enol rubidium that are filling the void between these octahedra. So if we modulate, or if we change the ratio of the composition of the perovskite, we can change the optical, the properties of the perovskite, the optical properties. So for example, if we are going from bromine to iodine to chlorine series, we are blue shifting the absorbance. And here in this case, you can see very clear that if we are increasing the amount of bromine, we are narrowing the band gap, and we are absorbing until only with 3 bromine here until 550 nanometers. And if this perovskite is all iodine, we can extend the absorbance until 850. On the other hand, if we change the A cation, the same thing happens. So Same, we can narrow the band gap just by changing the composition of the perovskite. So these perovskites are not new. They were known for so long. In 1987, Professor Dieter Weber published a paper in which they reporting the structure of this kind of perovskite, the methyl halide perovskites. And later on, Damien Mitzi, in a book chapter, he focused on the synthesis, the structure, and the properties of some of these materials. Well, perovskites are the material of choice for photovoltaics. The outstanding photovoltaic performance of perovskites relies on the exceptional intrinsic properties that they are showing. They are semiconductors with perovskite structure, showing long charge diffusion length with very low exciton binding energy, 25 millielectron volts at room temperature. This is very important because it can be processed from solution. They are showing low band gaps between 1.1 and 1.5 electron volts. As I said before, you can modulate the band gaps just by changing the composition, showing unique properties, optical properties. And this is also very important because they are showing good electrical conductivity with some bipolar charge transport. That means that can transport either electrons or holes. Well, continue with the crystal structure of the perovskite. We have different phases, and the one that is active for photovoltaic applications is the perovskite black phase. This perovskite black phase, as I said, is quite astringent to the relative ion size. So for example, if we are using too small or too big, too large cations, we are moving away from the 0.8 and 1.0 Goldmich tolerance factor. So we are moving away from the black phase perovskite. In this case, for example, the formamidinium lead iodide 3, it's very difficult to obtain the cubic structure because it is not stable. It's only you can obtain only at 150 degrees. On the other hand, methylammonium lead iodide does not have a yellow phase. Between the tolerance factor is 0.9, but this perovskite is not very stable because typically the methylammonium tend to leave the crystal structure. Further, we can modulate, we can engineer the composition of the perovskite just by adding different amounts of mixed cations. For example, using methylammonium and formamidinium, we are reducing the amount of impurity of yellow phase. And by adding another cation, such as cesium, we are reducing these impurities, and we can process this at room temperature, like a triple cation perovskite, which is nowadays the state of the art. Well, perovskites are sensitive to heat, to moisture, and ironically to light. So there are many channels of degradation, such as moisture, complexation, ion migration, related with thermal instability and thermal induced chemical decomposition and phase transition. So this is a solar cell that is sensitive to light, which is catastrophic because we need to obtain a stable perovskite if we want to go from academic sensation to industrial reality. We have to tackle the stability of the perovskites. And for doing that, the market is, as I said, the reference is crystalline silicon and is degrading at a rate of 0.5% per year. That ensure a 25 years operational conditions. This should be to compete with silicon, but at least perovskites have to be stable or to be considered as a potential commercialization, should at least keep their initial efficiencies after around 100 hours under 85 degrees at 85% relative humidity. The year has more than 8,000 hours. So back in 2017, the group of Professor Nasseruddin reported a perovskite that it was stable for 1 year, for more than 1 year, with efficiencies not higher than 12%, but this is unprecedented. I mean, this is extremely good because it's stable for 1 year. And for doing that, they use a 2D, 3D approach. What is this? This is Perovskite, we can reduce the dimensionality by adding longer or bulkier organic cations. So for example, we have these 3D perovskite that are corner-sharing metal halides, octahedra that extend in all 3 dimensions. So if we introduce bulkier or longer organic cations, we can reduce the dimension, we can obtain 2D perovskites that consist on a single or multiple seeds, inorganic seeds that are in between. Then we have the organic spacers. Also, we can have 1D perovskites that are, or perovskitoids that are corner sharing, edge sharing, and face sharing to form nanowires. And on the other hand, we can have 0D perovskite or perovskitoids that are isolated metal halide octahedra or can be considered as a clusters. So introducing these long organic cations provide hydrophobicity to the perovskite, and therefore there would be more resistive to moisture, and they are showing higher or better environmental stability. The only problem with this is that the 2D perovskite are showing lower efficiency, but at least if we combine them in just like in this manuscript, in this paper, as a bilayer, we can improve, on one hand, we can improve the stability in comparison with just the 3D, and even the long-term stability. Also, if we are using these 0D or 1D perovskitoids in combination with the 3D perovskite as well, we can improve not only the photovoltaic performance, these are the 3D, only the 3D with 22%, but if we are adding 1D, it goes from 22 to 23, almost 24, and in here to 24.5. But not only we are improving the efficiency, we are also improving the long-term stability. Well, another problem of perovskite is the lead containing. And the lead is one of the first documented poisoning in history. And the presence of lead is slowing down the pace of commercialization, or even can hinder that commercialization. So therefore, if we wanted to deliver sustainable technology, we have to get rid of lead. What are the choices? What are we can use lead-free compositions. So the basic one, the most used one, is the tin-based perovskite that offer the an optimum band gap of 1.2 to 1.4 electron volts that theoretically can outperform lead-based perovskite. The only problem with this is they are not reaching they are not reaching the efficiency or matching the efficiency of lead-based perovskite, and they are showing even lower stability than lead-based perovskites. Here I show you a graph in which these are different materials that have a band gap between 1.1 and 2 electron volts, and that can be potential candidates for photovoltaic applications. Well, among the advantages, I already commented on that. They are showing the perovskite can be processed at low temperature method. So that means that we will have very cheap cells with low energy requirements. Probably is one of the best challenger, if not the challenger, is to complement silicon. They show variable diffusion length of the exciton depending on the composition. So we can have 100 nanometers in the methylammonium lead iodine, and if we are doping with certain amount of chlorine, we can have until 1 micron diffusion length, just in contrast with the 10 nanometers of organic compounds. They are also, as I said, transport ambipolar behavior. They can transport electron and holes. They are showing VOCs always higher than 1 volt, and they are showing also promising stability that I will comment later. Well, when we're moving to device architecture, we can have 2 possible architectures. The first one is called the Mesoporous structure. That is, this structure is mainly coming from the dye-sensitive solar cells, in which we use a transparent conductive oxide On top of that, we deposit an electron transporting layer. Typically is another planar layer of titanium oxide. On top of the titanium oxide, we deposit mesoporous titanium oxide. Then the perovskite infiltrates the pores of this mesoporous titanium oxide. We use the whole transporting material, and finally we thermally deposit the electrode. These kind of devices were the first one reported with a 3.9%. And right now, the problem with this is the high temperature that we need to sinter in the titanium oxide, that is around 500 degrees. That increase the processing time and the cost of the cell production. On the other hand, we have planar structures in which we get rid of the mesoporous titanium oxide, following more or less the same structure, and they are showing very nice efficiencies right now, even comparable or higher than the mesoporous structure. They need lower energy requirements because they only to heat to different heating processes, the higher temperature is 150. They are easier to prepare and therefore less time consuming. So as I already mentioned, they are ambipolar, so we can combine the perovskite with the electron acceptor molecules or with electron donor molecules. So in that way, we will have NIP or conventional devices, normal devices, in combination with electron donor molecules, or we can have inverted devices, PIN, in which we combine with electron acceptor groups. Well, this is the first paper that was published in this field. It was published in 2009 by the group of Professor Miyasaka. And they use the approach of dye-sensitized solar cells. They use titanium oxide, they infiltrate the perovskite in this titanium oxide, and they use later on the redox pair of iodine, triiodine, liquid electrolyte. So in a very modest efficiencies, around 4%, but the problem was not the lousy or modest efficiency that they obtained. The problem was the stability, because the device didn't last for more than 5 minutes. Why? Because the liquid electrolyte degraded the perovskite. Well, this was a very relevant work, as you can see from the number of citations, more than 13,000 citations. Well, the next breakthrough in this field was to get to remove the liquid electrolyte and substitute for a solid material, solid electrolyte or solid whole transporting layer. In this case, this was a spiral method. So just by doing that, the efficiencies just jumped from 4 to 11% or to close to 10%. And this paper were published at the same, more or less at the same times by two different groups. This paper by the groups of Henry Knight, and this by the group of Professor Michael Gretzel. Well, emerging from this groundbreaking discovery, the groundbreaking discovery of perovskite as active material for perovskites for solar cells, for photovoltaic applications, scientific research has exploded in this field, leaving one of the hottest topics in science nowadays. And this topic is still hot, it's not slowing down, and the number of publications rapidly increased from 2009 until right now, that we are kind of reaching a plateau with more than 2,000 publications of perovskite solar cells. This kind of reminds to the same trend that we found on the graphene. Well, as whole transporting materials play a very important role in perovskite solar cells because they are in charge of injecting the holes or extracting the holes, transport them to the electrons to be collected. So we can have inorganic, polymeric, or small organic molecules, and these are the ones that I will focus this talk. Small organic molecules for whole transporting materials are probably the most studied ones. Potential candidates have to fulfill not very special requirements, such as transparent and indivisible, adequate homo energy, decent hole mobility, showing glass transition about 100 degrees, high solubility, and low cost. So this is the spiral method. That is the molecule that the group of Henry Knight, Michael Gretzel used to get rid of the iodine triiodine liquid electrolyte. And this is the one that is the reference compound for everybody in the world. Everybody in the world is using this as a reference to see how good or how bad they are making devices. This molecule is transparent, divisible, possess an adequate homo energy, is not showing a decent hole mobility in its pristine form. So it is showing TG higher than 100 degrees, excellent solubility. You can solubilize this 70 milligrams of this in 1 milliliter of chlorobenzene, but it's not showing already also a low cost, because 5 grams is close to 1,500 euros. So in order to improve the whole mobility, the whole transporting materials, some of them need need some dopants in order just to improve the whole mobility. This could be the lithium salt, and this cobalt complex are used to improve the mobility of the whole transporting materials. And TVP, it is a morphology controller. So here I show you some other representative examples from the literature that right now they are showing efficiencies higher than 20%. We have spirocycles, more spiro compounds. We have these linear molecules, all of them showing excellent performance, but still we are lacking of a relationship between the molecular structure and the photovoltaic performance. With this, I'm not saying that there is a relationship. At least we need to find a trend using the same central scaffold. So this is why we said at the very beginning, we set our eyes in this very large family of molecules that are called benzotrithiophenol or VTT molecule, that consists on 3 benzene rings that are fused to a central 3 thiophene rings, that are fused to a central benzene ring. Depending on this, the position of the sulfur atom, we can have 7 possible isomers. And regarding this position, we can have different properties. They are planar and sulfur-rich polycyclic aromatic hydrocarbons, showing a strong stacking through intermolecular interactions that may enhance the whole carrier mobilities. So we select BBB BTT1 just because the synthesis was easier than the other ones. And we employ different electron donor groups. So we use diphenylamine decorated in a carbazole, and triphenylamines. So the synthesis of these molecules started with this trichlorobenzene. We perform a 3-fold iodination reaction followed by a 3-fold sonogacira cross-coupling. In order to close the ring and form the thiophene rings, we use sodium sulfide and refluxing NMP, and finally we brominated at the alpha position of the thiophene. Finally, to introduce the different electron donor groups, we perform for BTT1 and BTT2, we perform a 3-fold Buchwald-Hartwig reaction. And in the case of BTT3, we perform a 3-fold Suzuki cross coupling. Well, we send these molecules to EPFL, to Professor Nasseruddin's group, and they made the devices for us. And you can see here the cross section of the device. We can modulate, or we can modulate the thickness of the whole transporting layer just by optimizing the concentration. So for example, the best thickness for BTT1 was close to 50 nanometers. For BTT2, it was 150, and for BTT3, it was around 100 nanometers. These whole transporting materials were combined with 2 different perovskites, with the methylammonium lead iodine that I said this is the most common one, displaying efficiencies very close to those reported by the reference compound, the spirometat. In the case of the BTT1, it was lower than that. If we see the mixed cation, mixed anion perovskite, which is this one, they are already also showing excellent performance close to that of Spiro. Again, the lower efficiency was obtained for BTT1. And why is that? Because the solubility, it was a big issue for this molecule. It was very difficult to dissolve, and for that the film forming ability, it was much lower than the other 2. Well, encouraged by these extraordinary results, we decided to continue exploring the isomerism effect on the photovoltaic performance. For that, we choose another two central scaffold, BTT central scaffold, and we introduce the same electron donor molecule that displayed the best efficiency with the methylammonium perovskite. Well, the synthesis of these molecules are quite different. So for BTT4, we started with this dibromothiophenol. We perform a two-fold steel coupling, then oxidative photocyclization. We get the BTT central scaffold. We brominated at the alpha positions of the thiophene rings. We perform a three-fold susucricose coupling just to get BTT4. For BTT5, the synthetic procedure was more challenging. We started with this dibromobistthiophene. We performed a two-fold sonovacilar cross coupling. And then to form the third thiophene ring, we used sulfur in the presence of the Wilkinson catalyst, and this is the key step because the yield of this reaction was not higher than 17%, if I remember correctly. Then we brominated at the alpha positions, and finally we perform a four-fold susucricose coupling. Well, as I said before, regarding the position of the sulfur atom, we can have different properties. So from the electrochemical measurements, we can see that BTT5 exhibit 4 oxidation waves. The first one, it is cathodically shifted, so it is a stronger electron donor, displaying a HOMO energy of estimate HOMO energy from solution of -5.18. BTT4, on the other hand, display just 1 or 2, depending on, and this is the central attribute to the central scaffold. We can see this first oxidation wave that is, it is not only one, it is a simultaneous process of 3 oxidation processes, and is the HOMO energy level was estimated to be -5.33, that it was very close to that of the BTT3. Well, from the optical properties, we can see that BTT5 is significantly redshifted due to the enhanced pi electron delocalization of the central scaffold of the BTT5, and BTT4 the absorbance is much broader than the BTT3 due to the the direct conjugation between these thiophene rings that are facing in the same direction. From here, we can estimate the optical band gap, and then we can estimate the energy of the LUMO. Well, we send this molecule to Professor Nasseruddin in Switzerland, as I said before, and we prepare a mesoporous structure with the mixed cation, mixed anion perovskite. Well, the results are collected in this table. As you can see here, BTT4 exhibit a 19% efficiency, and BTT5 exhibit at 18.2%. That both of them exhibiting better efficiency than their analogous BTT3 that it was previously reported. So why is that? We surmise that it is because that the sulfur atoms are facing in the same direction, so may further interact with the perovskite, allowing better hole extraction. So we have also measured the conductivity of these molecules, and as you can see here, the highest conductivity was obtained for BTT4, so it is in a good accordance with the results from the IV curves. This following by the BTT5, and the conductivity of BTT4 is 20 times higher than that of BTT3. Well, with an eye towards carrying a complete and systematic study, we wanted to explore the effect of introducing heteroatoms using the same central core. So for that, we prepare this BTP that consists on 3 pyrrole rings that are fused to a central benzene ring. This BTF that consists on 3 furan rings fused to a central benzene ring. And we prepare BTSE with 3 selenophenes that are fused to a central benzene ring. So these molecules display also different electrochemical properties. From here, we can see that BTF1 and BTS1 display only one oxidation waves that are 3 simultaneous oxidation process from each triphenylamine for an energy for an HOMO energy of minus 5.38, minus 5.4, more or less. And BTP is a stronger stronger electron donor properties with a first oxidation waves cathodically shifted by around 0.3 volts. And this corresponds to a HOMO energy level of minus 5.05. From the optical characterization, we can see that the absorbance is redshifted in passing from nitrogen to oxygen to sulfur and finally to selenium. So again, from the intersection between the absorbance and the emission, we can obtain the optical bandgap, and then we can estimate the energy of the LUMO. Sorry. So we prepare mesoporous devices using the mixed cation, mixed anion perovskite. And again, the best efficiency was obtained for 18.5% in the case of the BTSE with the selenium rings, showing an excellent field factor, current of 21.88 and a VOC of close to 1.7 volts. Well, combining different features to tailor potential candidates, we wanted also to explore modulating the pi conjugation of the central scaffold. For that, we select this core that is called antratetratiophenene, 4 thiophene rings that are fused to a central anthracene ring. This is a sulfur-rich polycyclic hydromatic hydrocarbon displaying 4 thiophenes, showing excellent whole carrier mobilities in offered devices, just the pristine one, following a very simple synthetic route with very high yields. And we wanted to study the influence on the adding alkyl chains, longer alkyl chains on the periphery of the triphenylamines. Well, this is the synthesis of these whole transporting materials. For getting 4, this molecule 4, it is very easy, quite straightforward. And more importantly, no column chromatography was needed. Just by washing, precipitating, you can obtain 4 in a gram scale. So we started with this tetrabromo-benzene. We performed 4-fold steel coupling, bromination at the alpha position of the thiophene rings, and finally Sol reaction using in the presence of iron chloride. Then we introduced the different triphenylamine with different lengths of the alkyl chains by a 4-fold succinct coupling. But just by introducing longer alkyl chains, it doesn't affect much the optical, neither the electrochemical properties. The big difference are coming when we are talking about photovoltaic performance. So we can see here that the ATT methoxy with the shorter alkyl chains display the highest efficiency, even higher than the spirometat. Upon increasing the length of the alkyl chains, the efficiency decreases. By measuring the conductivity of this whole transporting material, follow the photovoltaic trend, the conductivity. So we can see that the highest conductivity was found for the ATT methoxy, that is 2 orders of magnitude higher than the ATT with the longer alkyl chains. Well, just to finish, we wanted to go to move away from the flat land of these central cores, and we wanted to explore molecules with higher solubility. In this case, we select this spirotype whole transporting material based on phenoxazine and phenothiazine. If we study the synthesis with this phenoxazine or phenothiazine, we perform first a Buchwald-Hartwig reaction. Finally, we treat it with embuthil lithium and quench it with this ketone. We can obtain the spiranic core. Finally, we introduce the diphenylamines by a twofold Buchwald-Hartwig reaction in very nice yields. We prepare the devices. Two different kind of devices: the Mesoporous devices that were made in Switzerland, and these planar devices using the triple cation perovskite that were made in our laboratory at India Nanoscience. So from the UV cards, we can, from this table, we can see that Mesoporous, in the Mesoporous structure, the devices with our whole transporting material perform worse than the spiral method. But when we are moving to planar devices, we are getting efficiencies pretty much the same or even higher than the spiral method. But the more importantly, what we measured, it was the long-term stability of these devices. So in this graph, you have the long-term stability of devices in a dart drawer experiment. That is, keep the devices in a dart drawer and measure every 10 days or 5 days. And in here, you can see that our whole transporting materials are displaying better stability than those of a spiral method. And this is remarkable because they were stable for at least more than 300 days. It's almost a year. On the other hand, we have also measured the long-term stability of our whole transporting material under continuous light illumination in the Mesoporous structure. So showing again only a decrease of only 6% after 1200 hours. So this is also remarkable, showing that these devices exhibit excellent long-term stability and making these among the most stable doped whole transporting materials in perovskite solar cells. So why these molecules were more stable than the spiral method? We first see the contact angle measurements to see how our materials protect the perovskite against moisture. And as you can see from the contact angle, we can see the same, more or less the same angle. So they are showing the same, they are defending the perovskite more or less the same. So why is the difference? The difference are coming from the scanning calorimetry. So the pristine spiral method saw glass transition of 125 degrees. Our molecules exhibit higher temperature, 152 and 166. What happened? These are pristine whole transporting materials. What happened when we dope these materials with the TVP, what is one of the dopants used in the device? So in the case of the spiral method, this glass transition drops until 50 degrees. In the case of our molecules, drops until 90 degrees, making our molecules superior, showing superior thermal robustness and therefore reduced tendency to crystallize in comparison with the spiral method. So just to summarize, we prepare different, we use the same central scaffold, and we study different electron donated units. Also, we study isomerism effect on the photovoltaic performance, the heteroatoms influence, also using the same central scaffold. We have also extended the conjugation of the central scaffold. And finally, we study the long-term stability based on spiral type whole transporting materials. With this, I would like to thank the actors, Nazario Martin, my PhD students, Javier Urieta, that he is now a doctor, and also Ines, that he is already a doctor, and Luis Ilicachi, that came from Colombia to spend time with us, the group of Professor Nasseruddin, and the group of Professor Enrique Ortiz for the theoretical calculations, and thank you all for your kind attention.
Many thanks, Agus. A very nice lecture, and I think you went from the general things to more specific questions related with your research. So I think that it's time for questions. We already have one from Luis Sanchez, and Daniel Lozano is saying really nice talk also from the chat. Let me go for the first question. A second one is coming. I just read, wonderful talk, Agustin. Thanks a lot. One of the requested characteristics of the whole transporting layer is the cost, obviously. You have shown us a battery of really nice whole transporting layers, materials that exhibit remarkable performance regarding the power conversion. However, are these whole transporting layers comparable in price to the Spiro methoxy material? It is possible to think about a real application of any of these thiophene or new Spiro compounds you have shown us?
Thank you very much, Luis, for the question. Yeah, Spiro it's a very expensive whole transporting material, and we did like a kind of sheet of what was the cost of our whole transporting material, and it was extremely low. I think it was per gram around 20 to 25 euros. So we did an estimation with all the solvents need for the columns, all the silica gel, and everything. It was around 20 to 25%. And for the other part, we have a patent. We already patented some of these whole transporting materials, but still there are few of them that have been reported in the literature. There are right now commercial in TCI.
I think that with that fairly answer the question. A second question that we have here coming from Noemi Encinas, also from the house. She said, congratulations for this excellent talk and work regarding the moisture protection provided for perovskites. Did you check just water Ca? Have you thought on measuring water creeping through the top layer perovskite interface?
No, we didn't think about that. We did just the contact angle with dope Spiro without dopants, and also just on top of the perovskite. The perovskite that just dissolve from using water. But no,
that's something that maybe Noemi can help us to
do,
knowing her experience. So probably might be a field as might many times mentions in these presentations to look for an interface within different research experience. So in that sense, probably the experience of Noemi can help and look at the surface with on that aspect. Okay, and we have another question here coming from Juan Leon from our PhD program. Congratulations for your presentation, August. To which extent the introduction of multiple TPA groups can enhance the performance of small molecules as whole transporting materials? Or is it more determinant the nature of the core than the amount of donor functional groups?
Well, that's a good question.
Yeah,
because TPA, I mean, using different or introducing more triphenylamines or donor molecules will not affect the efficiency. Even with just two TPAs, you can obtain very nice efficiencies. And also the nature of the core, it may have some influence at some extent, because, for example, it is very important to try to control. If you can control the pp stacking of the molecule, you can enhance the conductivity of the molecules. But on the other hand, when you have Spiro compounds, that is completely different. I mean, I don't know why Spiro performs so well in comparison with other molecules, but for example, you can introduce, as I said, you can introduce just two different TPAs or diphenylamines, and the molecule will work exactly the same, very well. In this case, they are using a very high congested central big core. Maybe the influence of this sulfur, the lone pair of the sulfur can interact with the perovskite, which is very important parameter, and can enhance the whole extraction of the molecule. So everything has their influence. So not by adding more TPAs you will have more efficiency. But if you have a good design, you can obtain a good efficiency. Yeah, of course.
Yeah, actually, it's very nice to see how you, at the end, have some trends on the behavior of the different families, and it's not so easy to control or to look to the relationship between the properties and the molecular design, considering all the engineer of the device. In that sense, and the last part of your talk, because I enjoy particularly, and I found the ATT molecule series quite straightforward to synthesize, as you mentioned, and about the bulkier or the alkyl change, to which extent the morphology, which are the conclusions on the morphology, if you can be more general in that part. Which is the influence of the chain at the end?
The chain is the film forming ability. We are increasing, for example, when we have shorter alkyl chains, it is very difficult to dissolve. So for example, we need to heat the molecule until 100 degrees and deposit on the device that is also heated at 100 degrees, because if not, it will precipitate very fast. But doing that, we can get very nice and very smooth films of ATT with methoxy. On the other hand, when we are introducing longer alkyl chains, the problem is coming also to prepare a good film, a smooth film, but it's also coming from the thermal properties of the molecule. Because when you have a decyl group, you are not getting just one glass transition. You are getting 4 glass transitions, different glass transitions, and not at 100 degrees, 120. These are at 50 degrees. So this will affect the final performance of the device. On the other hand, when you have a C4, butoxy group, it's working more or less the same. We can say that it's just 1%, but the thing that have to be is the formation of the film, yeah. And also introducing longer alkyl chains, you are affecting the conductivity as well.
Okay, so you have a good idea of what's going on.
I have here I don't know. No, I don't have the TG.
Okay, I'm going to more general questions regarding the technology. You find feasible to have perovskite devices soon in the market? I think so, or even maybe hybrids. I don't know if it's possible, because I don't know if from the technology that we have from silicon, basically, we can use that technology to build the perovskite devices, or even think in hybrid devices. How you envision the field?
Yeah, there are few companies that are commercializing perovskite, but I think they're not still a panel of perovskite. The companies are Oxford PV, that is a company that was built from Professor Henry Knight, and the other company, it is from Poland. I don't remember right now the name. It was a former student of Hem Bolling, the CEO of this company. There are also in here you can see, I don't know, in the PV chart you can see that there are see here. These are let me just present. Here you can have this 29.8 the efficiency. It's a tandem with silicon, or perovskite with silicon. For heating the market, I think right now there are not solar cells made of perovskite in the market because of the regulations about the LED. But yeah, in the near future, I think we can see, of course, perovskite. There are some other applications that right now are still in progress, and is like using perovskites in the space for aerospatial application. So we are in collaboration with people at India to try to send a proof to Mars with perovskites, solar cells there, because they can be folded and you can just roll it down in the. But we are still working on it.
But very interesting indeed. Okay, and
I have a question.
Okay. Then I give you the turn. Okay, of course, if possible.
Well, I am an experienced person in this field, but I want to ask you from my biochemistry point of view. No, when you try to select which components have your material, your perovskite. Do you think about, for instance, the toxicity aspects or the waste processing aspects or the average life of these materials? I mean, it's something that you if these materials are the fragility of this material. I mean, this kind of things are aspects that you handle in order to select which are your components of your material?
This was this perovskite were I mean, the evolution of the perovskite started with this with the methylammonium lead perovskite that was unstable because methylammonium tend to leave the crystal structure of the perovskite, and then you are getting lead iodide at the end. So with the waste, we are all of the devices that we make with this perovskite, we store them and we send it to dispose them in a proper way. Then about the research of a lot of people doing these kind of perovskite. So we started with this methylammonium. Then the mixed cation, mixed anion seems to be the one that it was even more stable than the other one, because now we have formamidinium in the structure, so it's not so easy for methylammonium to leave the structure. And then just by adding cesium, and we have the triple cation, that perovskite, it is much more. In our case, we saw that it is much stable. And also, if you're just combining to protect the perovskite against moisture with 2D or low dimensional perovskites, this will be very stable. I mean, for example, the devices that the molecules that I saw you at the end, these are the actual devices. And here you have the Mesoporous structure, the Mesoporous devices. They are using thicker film, thicker glass. And these are the planar ones because they are using thinner glass. So these devices, if your perovskite is degrading, so you can see that the color change from this to obtain something yellow. You are going from something that is brown or to something yellow. And in our case, it didn't degrade much because it was stable for almost 300 days. That was something good coming from the COVID, because we measured. This is the last day we measure, and then following the first day that we went to the lab, we measured again, and it was quite stable, our devices.
Okay, I don't know if Maite has so the questions. If not, we have one coming through the chat, not through the other place, but doesn't matter. Maybe I can read. It's coming from Patricia Izquierdo, also from the PhD program in organic chemistry here from the chemistry faculty. She said, very nice talk, as there is not an obvious relationship between conjugated core. She asked about if the individual TPA molecules with methoxy groups provide results, if you have tried that, or you always need a conjugate core.
We never tried that, but there are a few groups not using just the TPA just by the triphenyl. I mean, just by using a small, like a donor acceptor system, a TPA with a carboxylic group, the kind of molecule that you use in disensitized, and it was like around very good performance at 17-18%. but TPA as it is, I don't think it's gonna work. It's going to work. I don't know why, but it's not going to work probably. You need to add this triphenylamine to something else. You need to link it to a central benzene, I don't know, thiophene, something else. If not like that, because I don't know if she meant with 3-O-methoxy but yeah, I don't think it's gonna work. But yeah, and it's not done. That is not done, of course.
Okay. Well, I think that we have to finish this talk. I think that was a nice talk. I learned a lot. I always learn a lot because there are very different topics, and it's nice to have all of your research so visible. Then I encourage everybody to be in the next talk of Gabriel Piedrafita from the Biochemistry Department. And well, I say thank you, everybody. Thank you, Agustin. Thank you, Maria Ángeles. And thank you all the attendance. Okay, see you next Thursday.